close your eyes and imagine a world you've never seen, not because it's far away, but because it vanished 12,000 years ago. A world so alien, so impossibly different from today, that if you were dropped into it, you wouldn't recognise Earth at all. The year is 10,000 BCE. Ice sheets tower over the northern continents, miles thick, heavier than mountains, grinding slowly southward like frozen bulldozers reshaping the world. In North America, ice covers everything from the Arctic Ocean down to where New York City will one day stand. In Europe, glaciers bury Scandinavia, Britain and most of Germany under crushing walls of white. The weight is so immense that the continents themselves are pressed down, sagging under billions of tons of frozen water. The oceans are 400 feet lower than today, not 40 feet. 400! Walk where Miami's beaches will someday be, and you're 60 miles inland. The English Channel doesn't exist. Britain and France are connected by rolling grasslands. Indonesia isn't a chain of islands, it's part of mainland Asia. You could walk from Siberia to Alaska, across a land bridge wider than Texas. And the cold, the brutal, relentless cold that defines everything. Average global temperatures are 10 to 15 degrees Fahrenheit lower than today. That might not sound like much, but it's the difference between civilization and ice age, between cities and survival. But here's what makes this world truly breathtaking. The animals. Creatures so massive, so powerful, they make today's wildlife look tame. Woolly mammoths, 13 feet tall at the shoulder, with curved tusks 15 feet long, roaming in herds across the frozen grasslands. Giant ground sloths the size of elephants, standing on their hind legs to strip branches from trees. Saber-toothed cats with 8-inch fangs, perfectly designed for puncturing thick hide and massive muscle. Cave bears that weigh 3,000 pounds, dire wolves hunting in packs of dozens, enormous bison with horn spans of 7 feet, terror birds, flightless predators 10 feet tall with beaks like axes. This is the Pleistocene world, Earth's last ice age, a planet locked in deep freeze for over 100,000 years, and living in this frozen wilderness scattered in small bands across the habitable zones are humans, your ancestors. Not primitive cave people fumbling in the dark, but sophisticated hunters with complex tools, elaborate clothing, art and culture. They've adapted to the Ice Age so completely that this frozen world is all they know. It's home. If you're using this to fall asleep, that's exactly why I make these. So maybe subscribe and tell me, where are you right now and what time is it? I read the comments and it's fascinating. Tokyo at sunrise, London at lunch, Los Angeles at midnight, all watching the same story unfold. Drop a comment. I'm genuinely curious where in the world you are right now. So humanity is thriving in the Ice Age. Animals are thriving. The world has found a brutal but stable equilibrium, and then, about 12,000 years ago, something changes. Something triggers an event so catastrophic, so rapid, so completely overwhelming that it will reshape every inch of the planet within a few human lifetimes. The ice begins to melt, not slowly, not gradually, in geological terms, almost instantly. Within a few thousand years, sometimes within mere centuries, those mile-thick glaciers start collapsing. Ice sheets that took 100,000 years to build begin disintegrating in a cosmic blink. The meltwater has to go somewhere. Imagine the largest floods in recorded history, then multiply them by 1,000, by 10,000. Walls of water hundreds of feet high, exploding across continents, lakes the size of seas bursting through ice dams and draining in weeks, coastlines drowning as oceans rise 400 feet, swallowing thousands of square miles of land where humans had lived for generations. And in the chaos, in the rapid transformation from ice world to the Earth we know today, something else happens. The giants die. Within a few thousand years, almost every large animal on the planet goes extinct. Mammoths, gone. Giant sloths, gone. Saber-toothed cats, terror birds, cave bears, dire wolves, massive bison, all gone. Over 150 species of megafauna, creatures that had survived multiple ice ages, that had thrived for millions of years, just vanish from the fossil record. This is the most dramatic extinction event since the asteroid that killed the dinosaurs. Except there was no asteroid, no single catastrophic impact, just ice melting and seas rising, and something about that transformation killed the giants. But not humans. Somehow, impossibly, humans not only survived this planetary catastrophe, we thrived. We adapted. We exploded across every continent. And within a few thousand years of the Ice Age ending, we invented agriculture, built cities, created civilization. Everything you see around you, every bit of human achievement, traces back to what our ancestors did right at the moment the Ice Age ended. So what triggered the melt? Why did temperatures suddenly spike after 100,000 years of stability? What caused floods so massive they reshaped continents? Why did giant animals that had survived countless climate changes suddenly go extinct? And how did humans, relatively small and physically weak compared to the megafauna, not just survive but inherit the Earth? The answers are written in ice cores from Greenland, in sediment layers at the bottom of ancient lakes, in the scattered bones of extinct giants, and in the genetic code of every person alive today. This is the story of the most important climate transformation in human history. The moment when Earth stopped being an ice planet and became the world we know. This is what happened when the Ice Ages ended 12,000 years ago. 20,000 years ago, Earth was a completely different planet. Not metaphorically different. Actually physically, fundamentally transformed from the world we know today. If you could somehow travel back in time to that moment, you'd barely recognise it as the same place. This was the last glacial maximum, the coldest, iciest period of the most recent ice age, and the world our ancestors inherited after their long evolutionary journey. Let's start with the ice itself, because that's what defined everything about this period. The sheer scale of the ice sheets that covered the planet is almost impossible to comprehend. We're not talking about glaciers in mountain valleys or ice caps at the poles. We're talking about continental ice sheets, miles thick, covering millions of square miles, reshaping entire landscapes under their incomprehensible weight. The Laurentide ice sheet alone, centred on Hudson Bay, covered virtually all of Canada and stretched deep into what's now the northern United States. Imagine ice from the Arctic Ocean all the way down to New York, to Pennsylvania, to the Great Lakes region. In some places this ice was over 2 miles thick. 2 miles of solid ice pressing down on the bedrock, warping the Earth's crust beneath it, grinding mountains into powder, scouring valleys hundreds of feet deep. Meanwhile, across the Atlantic, the Fennoscandian ice sheet blanketed northern Europe. Britain, Scandinavia, northern Germany, Poland, all buried under ice. The weight was so tremendous that Scandinavia is still rebounding from it today, rising measurably each year as the land slowly returns to its original shape, 10,000 years after the ice finally melted. Asia had its own massive ice sheets covering Siberia and the mountain ranges of the interior. The Himalayas carried glaciers that made modern mountain ice fields look like decorations. South America had ice sheets extending far north from Antarctica, covering Patagonia and the southern Andes. All this ice represented something extraordinary. Earth's water doesn't disappear, it just changes location. Every drop of water locked up in those continental ice sheets had come from somewhere, and that somewhere was the ocean. Sea levels during the last glacial maximum were approximately 400 feet lower than today. 400 feet. Let that sink in. The entire geography of Earth's coastlines was completely different. This massive drop in sea level exposed enormous areas of what's now ocean floor as dry land. These weren't just narrow strips of beach. They were vast territories, entire subcontinents that don't exist anymore. In the north, a landmass called Beringia connected Asia and North America where the Bering Strait is today. But Beringia wasn't just a bridge. It was a massive territory, maybe 1,000 miles from north to south, a completely distinct ecological zone that supported its own unique communities of plants and animals. Between Britain and continental Europe stretched Doggerland, a low-lying plain that connected what are now islands into a continuous landscape. Archaeological evidence suggests this was prime territory for Ice Age hunters, rich in resources, crisscrossed with rivers, home to massive herds of grazing animals. In Southeast Asia, the exposed continental shelf created Sunderland, connecting Indonesia, Malaysia and the Philippines into a single enormous landmass. Australia and New Guinea were joined as Sahul. The Mediterranean was smaller. The Persian Gulf was a river valley. The entire map of Earth looked alien. But it wasn't just the ice and exposed land that made this world different. The climate itself had been fundamentally restructured. The massive ice sheets created their own weather patterns, distorting atmospheric circulation in ways that affected the entire planet. The jet streams, those rivers of fast-moving air that guide weather systems across the continents, were pushed far south by the presence of the ice. This meant that regions that are temperate today experienced Ice Age conditions then. Southern Europe, normally mild and Mediterranean, had a climate more like modern Scandinavia. The Sahara Desert, which today is one of the driest places on Earth, had a completely different rainfall pattern. Parts of what's now endless sand supported grasslands and scattered trees. The Amazon rainforest, that great engine of global biodiversity, was reduced to scattered refuge areas separated by dry savanna. Ocean currents were different too. The great oceanic conveyor belt that redistributes heat around the planet followed altered pathways. Cold water from melting ice edges created nutrient-rich upwellings in different locations, changing where fish populations concentrated, which affected where seabirds nested, which influenced coastal ecosystems in cascading waves of transformation. This was a world of extremes. Seasonal variations were more dramatic than anything we experience today. Winters in the Ice Age steppe could last 8 or 9 months, with temperatures that would kill an unprotected human in minutes. Summers were brief, but intensely productive, an explosion of plant growth and animal activity compressed into a few short weeks, when everything that was going to survive and reproduce had to do it fast. And in this transformed world, a completely unique ecosystem had emerged. This wasn't just a colder version of modern environments. It was something that has no real parallel in today's world. The Mammoth Steppe, as scientists call it, stretched in an almost continuous band from Spain to Canada, the largest biome in Earth's history. Imagine endless grasslands, but not like the African savanna or the American prairie. This was colder, drier, more open. Scattered stands of hardy trees, mostly conifers, broke up the landscape. In the summer, wildflowers would briefly carpet the ground in explosions of colour. In winter, everything turned to frozen wasteland where only the toughest organisms could survive. And what organisms they were. The megafauna of the Ice Age, the great animals that dominated this frozen planet, they were unlike anything alive today. They weren't just cold-adapted versions of modern species. They were something else entirely. Products of hundreds of thousands of years of evolution in Ice Age conditions. The most iconic, of course, were the woolly mammoths. These weren't just hairy elephants. They were perfectly engineered Ice Age survival machines. Standing up to 13 feet tall at the shoulder, covered in 2 layers of hair, the outer layer reaching nearly 3 feet long in some individuals, with curved tusks that could exceed 15 feet in length. Those tusks weren't just weapons or displays. Mammoths used them as tools, sweeping snow aside to reach vegetation underneath, breaking through ice to access water, even fighting off predators. Mammoth social structure was similar to modern elephants, matriarchal herds of related females and their young, males forming bachelor groups or living solitary lives. But their behaviour was adapted to the extreme seasonality of the Ice Age world. They had to migrate constantly, following the brief pulse of plant growth across vast distances, their movements timed to the seasons with precision born of evolutionary necessity. And they weren't alone. Woolly rhinoceros, equally impressive, equally adapted, roamed the same grasslands. These were massive animals, some weighing over 6,000 pounds, with 2 horns, the front one reaching over 3 feet long in the largest individuals. Like mammoths, they were covered in thick woolly coats. Unlike mammoths, they were solitary and apparently more aggressive. Cave paintings and preserved remains suggest they were formidable animals that even the largest predators approached with caution. Speaking of predators, the Ice Age had produced carnivores that would make modern big cats look modest. Saber-toothed cats, multiple species of them actually, had perfected the art of killing megafauna. Their famous elongated canines, reaching 7 inches in some species, weren't for biting in the way modern cats bite. They were precision instruments for severing blood vessels and windpipes. A saber-tooth would grapple its prey, use its powerful neck and shoulder muscles to stabilise the target, then deliver a surgical strike to vital areas with those specialised teeth. Cave lions, larger than any lion alive today, hunted in prides across Europe and Asia. Their prey base was different from modern lions. They targeted young mammoths, bison, horses, even rhinos when they could catch them vulnerable. Skeletal evidence shows incredible power. Cave lion bones are denser and more robust than modern lions, suggesting animals capable of bringing down prey that would be impossible for today's predators. In North America, dire wolves hunted in packs across the Ice Age landscapes. These weren't just big wolves, they were a distinct species, more heavily built than modern grey wolves, with bone-crushing jaws adapted for a different hunting strategy. While modern wolves rely on endurance and pack coordination to exhaust prey, dire wolves were more like hyenas, using raw power and strong jaws to disable and consume prey, including cracking bones to access marrow. And the prey they hunted, besides mammoths and rhinos, included an astonishing diversity of megafauna. Giant ground sloths, some species reaching 20 feet long when standing upright, browsed on trees and shrubs. These weren't slow, clumsy animals, despite their name. Reconstruction suggests they were formidable, with powerful arms tipped with massive claws, capable of defending themselves against even the largest predators. Glyptodonts, basically enormous armadillos the size of small cars, were protected by shells made of thousands of bone plates fused into armour that could stop most predators. Giant beavers, 8 feet long, built dams and lodges in Ice Age rivers. Massive bison, with horn spans reaching nearly 7 feet, moved in herds across the grasslands. Cave bears, distinct from modern bears, hibernated in European caves. Their population so dense that thousands of individual bears used some cave systems over the millennia, leaving layer after layer of remains. These were mostly vegetarian despite their size and power, but their sheer mass made them dangerous when disturbed. In Australia, the megafauna was even more bizarre. Diprotodon, the largest marsupial that ever lived, looked like a gigantic wombat, weighing over 6,000 pounds. Thylacoleo, the marsupial lion, was possibly pound for pound the most powerful predator that ever evolved, with a bite force that exceeded even that of saber-toothed cats relative to body size. This entire ecosystem, from the smallest rodents to the largest mammoths, was intricately balanced. The megafauna weren't just inhabitants of the Ice Age world. They were ecosystem engineers, actively shaping their environment. Mammoths knocked down trees, maintaining the open grassland environment that supported the herds. Their dung fertilized the soil and spread seeds across vast distances. When they died, their enormous carcasses provided food for scavengers and returned nutrients to the soil in concentrated doses. The grasslands themselves were unlike anything that exists today. Modern tundra is often marshy and waterlogged, supporting limited vegetation. The Ice Age steppe was drier, more productive, capable of supporting the enormous biomass of animals that depended on it. The combination of cold temperatures, low rainfall, and constant grazing pressure created a unique plant community dominated by hardy grasses, sedges, and herbs that could survive both the long winter freeze and the intensive grazing of millions of herbivores. And into this world, human beings had successfully inserted themselves, not just surviving on the margins, but thriving as apex predators and one of the most successful species on the planet. By 20,000 years ago, humans had spread across virtually every Ice Age environment, from the edges of the continental ice sheets to the tropical regions that had remained warm. But the humans living through the last glacial maximum were different from us in important ways. Not biologically. They were anatomically modern, with the same cognitive abilities we have today. But culturally, they had become specialists in Ice Age survival, developing technologies and strategies that made them perhaps the most formidable predators the planet had ever seen. In Europe, people were building sophisticated shelters from mammoth bones. These weren't crude windbreaks. They were engineered structures using hundreds of bones carefully selected and arranged, covered with hides, insulated with earth and turf. Some of these shelters were substantial enough to support multiple families through entire winters. Archaeological sites show evidence of central hearths, storage areas, even specialised activity zones for different tasks. The technology of Ice Age hunters was astonishingly sophisticated. Spear points were crafted with techniques that modern flint knappers struggle to replicate. The best examples show understanding of stone fracture mechanics that rivals modern materials science. They weren't just chipping rocks randomly. They were carefully shaping cores, removing precise flakes in predetermined sequences, creating weapons that combined maximum effectiveness with efficient use of raw materials. Atlatls, spear throwers that worked like extensions of the human arm, multiplied throwing power dramatically. A skilled hunter with an atlatl could launch a spear over 100 yards with enough force to penetrate thick hide. This meant humans could kill dangerous animals from safer distances, reducing the risk inherent in hunting megafauna. They developed specialized tools for processing kills, carefully designed scrapers for hide preparation, bone needles for creating fitted clothing, engraving tools for decorating objects with symbolic designs. Each tool represented generations of accumulated knowledge, refined techniques passed down and improved upon. But perhaps their most important innovation was social. Ice Age humans lived in larger, more interconnected groups than their ancestors. They maintained trade networks that moved raw materials hundreds of miles. Flint from specific quarries shows up in tools at sites separated by weeks of travel. Seashells from the Atlantic coast appear in inland European sites. Amber from the Baltic is found in southern France. This networking meant more than just material exchange. It meant information sharing. A technique developed by one group could spread across thousands of miles within a generation. Innovation could accumulate faster than ever before. When someone figured out a better way to treat hides, or a more effective hunting strategy, or an improved shelter design, that knowledge could propagate through the entire human population. They were also developing sophisticated symbolic culture. Cave paintings from this period show remarkable artistic skill and deep observation of animal behaviour. The famous paintings at Lascaux and Chauvet caves in France weren't crude stick figures. They were nuanced, dynamic representations that captured the essence of Ice Age animals with accuracy that demonstrates intimate knowledge of these creatures. Carved figurines, musical instruments made from bone and ivory, decorative beads and pendants all suggest people who had time for more than just survival. They were creating culture, passing down traditions, developing distinct group identities. Different regions show different artistic styles, different tool-making traditions, suggesting the emergence of what we might recognize as ethnic or cultural groups. And they were successful, wildly successful. Human populations during the last glacial maximum numbered in the hundreds of thousands, maybe even low millions globally. They occupied every major landmass except Antarctica. They had mastered environments from the Arctic to the tropics. They were hunting the largest, most dangerous animals on the planet and winning consistently. But their success existed in a precarious balance. The entire Ice Age ecosystem, with all its magnificent megafauna, all its vast grasslands, all its carefully adapted species, depended on one critical factor remaining constant: the ice. As long as the climate stayed cold, as long as the ice sheets remained stable, as long as the mammoth steppe persisted, this world could continue indefinitely. Species had been evolving in Ice Age conditions for hundreds of thousands of years. Humans had been perfecting Ice Age survival strategies for millennia. The frozen planet had become the normal planet. This was just how the world was. The humans living 20,000 years ago had no memory of any other climate. Their great-grandparents and their great-great-grandparents going back hundreds of generations had known only the Ice Age. The skills they practiced, the animals they hunted, the plants they gathered, all of it was perfectly tuned to this frozen world. But deep in the ice cores of Greenland, in the sediment layers of ancient lakes, in the growth rings of long-dead trees, a change was coming. Subtle at first, almost imperceptible. Slight shifts in solar radiation patterns, minor variations in atmospheric circulation, small changes in ocean currents. Individually, these changes meant nothing. Together they represented the beginning of a transformation that would be so rapid, so dramatic, so utterly complete, that it would destroy the Ice Age world forever and reshape the planet into something entirely new. The frozen planet, which had seemed eternal, was about to discover it was anything but, and the species that had adapted so perfectly to Ice Age conditions, including the most adaptable species of all, were about to face a test unlike anything their ancestors had survived. The great thaw was beginning. So there they were, 20,000 years ago. Modern humans, the sole survivors of 3 human species that had emerged from that ancient bottleneck. They had spread across the planet from the southern tip of Africa to the frozen steppes of Siberia. They had developed complex languages, sophisticated tools, and social networks that spanned continents. They were perfectly adapted to the Ice Age world. And then everything started to change. The trigger wasn't obvious at first. There was no single moment when the Ice Age decided to end. No dramatic event that announced the transformation to come. The climate had been fluctuating for hundreds of thousands of years. Warm periods followed by cold snaps followed by brief respites. The humans and animals living through it had no reason to think this time would be any different. But it was different. Catastrophically different. The real cause of what was about to happen began not on Earth, but in the geometry of Earth's orbit around the Sun. It's one of those beautiful cosmic accidents that shapes everything about life on our planet, yet remains completely invisible to anyone living through it. Scientists call them Milankovitch cycles, named after the Serbian mathematician who first figured them out in the 1920s. There are 3 of them, 3 different ways that Earth's orbit and rotation shift over time, changing how much solar radiation hits different parts of the planet. First, there's eccentricity. Earth's orbit around the Sun isn't a perfect circle. It's an ellipse, sometimes more circular, sometimes more elongated. This cycle takes about 100,000 years to complete. When the orbit is more elliptical, Earth's distance from the Sun varies more dramatically over the course of a year, intensifying seasonal differences. Second, there's obliquity, the tilt of Earth's axis. Right now, we're tilted at about 23.5 degrees, but that angle isn't constant. It varies between 22.1 and 24.5 degrees over a cycle that takes 41,000 years. More tilt means more extreme seasons, less tilt means milder ones. Third, there's precession, the slow wobble of Earth's axis. Like a spinning top that's starting to slow down, Earth wobbles as it spins. This wobble takes about 26,000 years to complete a full cycle, and it determines which hemisphere is tilted toward the sun during which part of Earth's orbit. None of these cycles is particularly dramatic on its own, but when they line up, when all three happen to reinforce each other, they can push Earth's climate into or out of an ice age. For the past 2.5 million years, these cycles have been driving the planet through repeated glacial and interglacial periods. Ice ages would build up slowly over tens of thousands of years as the cycles aligned to reduce summer sunshine in the northern hemisphere. Less summer sun meant winter snow didn't fully melt. Year after year the snow accumulated, compressed into ice, and eventually formed the massive ice sheets that covered half the continents. But the cycles didn't stop. They kept turning, kept shifting, and eventually they would align the other way. More summer sunshine hitting the northern hemisphere. Slightly warmer temperatures, just enough to start melting the ice sheets at the edges. Around 19,000 years ago, that's exactly what started happening. The orbital geometry had shifted to a configuration that delivered more solar radiation to the northern hemisphere during summer. Not a lot more, maybe 5% compared to the coldest periods, but it was enough. The ice sheets that had been growing for over 100,000 years finally stopped advancing. The leading edges, those massive walls of ice that had been grinding south year after year, began to stabilize. For a few thousand years, not much happened. The ice sheets weren't growing, but they weren't dramatically shrinking either. They just sat there, enormous and apparently permanent features of the landscape. A human living through this period would have noticed nothing unusual. The world was still frozen, winters were still brutal, the ice was still there, dominating the horizon like it always had. But underneath, things were changing. Summer melt was starting to exceed winter accumulation. Not by much, just a few centimetres per year at first, but those centimetres added up. Meltwater began trickling from the edges of the ice sheets. Small streams became rivers. Rivers carved channels through the landscape, channels that would carry even more meltwater as the melting accelerated. By 18,000 years ago, the retreat was undeniable. The ice sheets were shrinking. Sea levels began rising as locked-up water returned to the oceans. The process was slow, almost imperceptible on human timescales. Maybe a metre of sea level rise per century, maybe 2 kilometres of ice sheet retreat per year. Nothing that would alarm anyone living through it. But it was happening. The great thaw had begun. Then came the moment when everything should have continued smoothly toward our modern warm period. The Milankovitch cycles were set. The ice should have just kept melting steadily for the next several thousand years, but instead something completely unexpected happened. 12 through 900 years ago, right in the middle of this warming trend, the planet plunged back into ice age conditions. In a matter of decades, possibly years, temperatures in the northern hemisphere dropped back to near glacial levels. The ice sheets that had been retreating suddenly stopped. In some places they even started advancing again. Scientists call this the Younger Dryas, named after a small Arctic flower that suddenly reappeared in pollen records from this period. The name makes it sound gentle, even pretty. It was neither. The Younger Dryas was a climate catastrophe, a 1,000-year interruption in the warming that should have been impossible according to the orbital cycles, and nobody knows exactly what caused it. That's not quite true. We have theories, several of them, but the evidence is contradictory, controversial, and in some cases, downright bizarre. The Younger Dryas is one of the great mysteries of paleoclimatology, and solving it matters because whatever triggered it could potentially happen again. The most widely accepted theory involves the North Atlantic and the Great Ocean Conveyor Belt that circulates water around the planet. This circulation system depends on density differences. Warm, salty water from the tropics flows north toward the Arctic, cools down, becomes denser, and sinks to the ocean floor. That sinking drives the entire conveyor belt, pulling more warm water north to replace what sank. But what happens if you suddenly dump massive amounts of fresh water into the North Atlantic? Fresh water is less dense than salt water. It doesn't sink as easily. If you flood the North Atlantic with enough fresh water, you can shut down the entire circulation system. Around the time the Younger Dryas began, there was an enormous glacial lake sitting in the middle of North America, Lake Agassiz, named after the geologist who discovered evidence of it. This wasn't a normal lake. At its maximum extent, it was larger than all the modern Great Lakes combined. It contained more water than all the lakes on Earth today put together, and it was held back by a massive dam of ice. The theory goes like this. As the ice sheets melted, this ice dam weakened. Then, around 12,900 years ago, it failed catastrophically. Lake Agassiz emptied into the North Atlantic in a matter of months, maybe weeks. Imagine all that fresh water, hundreds of thousands of cubic kilometres of it, suddenly pouring into the ocean. The resulting flood would have been biblical in scale, and it would have done exactly what the theory predicts, shut down the ocean conveyor belt, plunging the northern hemisphere back into cold conditions. The problem is the evidence doesn't quite fit. Some sediment cores from the North Atlantic show the right kind of freshwater flooding at the right time. Others don't. The timing is fuzzy, and there's evidence that Lake Agassiz had drained eastward into the Atlantic before the Younger Dryas started, not during it. So some researchers have proposed more dramatic triggers. In the early 2000s, a team of scientists presented evidence for something that sounds like science fiction, an asteroid impact. They found a layer of sediment dating to the start of the Younger Dryas that contained unusual materials. Nanodiamonds, tiny particles that form under extreme heat and pressure. Platinum and iridium in concentrations much higher than normal. Magnetic microspherules, little beads of melted rock. And most intriguingly, hexagonal diamonds that can only form during hypervelocity impacts. Their interpretation. Around 12,900 years ago, a comet or asteroid broke up in Earth's atmosphere and exploded over the North American ice sheet. The impact, or more likely series of impacts, melted enormous amounts of ice, caused widespread wildfires, and threw enough debris into the atmosphere to block out sunlight and trigger rapid cooling. The hypothesis is controversial, to put it mildly. Other researchers have questioned whether those unusual materials really require an impact to explain. Nanodiamonds can form in wildfires. Platinum anomalies might come from volcanic eruptions. The hexagonal diamonds, some scientists think they're actually just terrestrial materials that were misidentified. But the impact hypothesis refuses to die because it keeps finding new evidence. Impact proxies show up in sediment cores from multiple continents. There's evidence of widespread burning across North America at exactly the right time. And there's a curious correlation. Many of the large mammals that went extinct during this period disappeared right at the Younger Dryas boundary. Then there's the volcanic theory. Some researchers point to massive eruptions during this period, events that could have injected enough sulfur dioxide and ash into the stratosphere to cool the planet significantly. There's evidence of major volcanic activity in Iceland, Indonesia, and Central America during the crucial time window. But here's what makes the Younger Dryas so frustratingly mysterious. Maybe they're all right. Maybe it wasn't one trigger, but a perfect storm of multiple factors hitting at once. Orbital cycles setting up vulnerable conditions, ice sheet collapse flooding the North Atlantic, an asteroid impact adding extra chaos, volcanic eruptions amplifying the cooling. All of it happening within a few centuries, maybe even a few decades. Whatever started it, once the Younger Dryas cold snap began, feedback loops took over and amplified everything. This is where climate science gets truly terrifying, because it shows how quickly things can spiral out of control once certain thresholds are crossed. The most important feedback involved ice and snow. Fresh white surfaces reflect sunlight back into space. Scientists call this the albedo effect. When the planet started cooling during the Younger Dryas, snow and ice began covering areas that had been bare ground or tundra. Those new white surfaces reflected more sunlight, cooling things further, allowing even more snow and ice to accumulate, which reflected even more sunlight. A runaway cooling spiral. Then there was the permafrost feedback, though this one ran in the opposite direction once the cold snap ended. Permafrost, permanently frozen soil, contains enormous amounts of organic matter, dead plants and animals that froze before they could fully decompose. When permafrost thaws, microbes wake up and start breaking down that organic material, releasing methane and carbon dioxide. Methane is a greenhouse gas about 25 times more potent than carbon dioxide. When the warming resumed after the Younger Dryas ended, massive amounts of permafrost started thawing across Siberia, Canada and Alaska. The resulting methane releases would have accelerated the warming dramatically. Ice cores from Greenland show atmospheric methane concentrations nearly doubling during the period right after the Younger Dryas ended. Ocean circulation was another feedback loop. When the North Atlantic circulation shut down during the Younger Dryas, it didn't just cool the Northern Hemisphere. It also shifted tropical rainfall patterns, changed wind patterns across the Atlantic, and even affected monsoon systems in Asia and Africa. When circulation resumed, all those patterns shifted again, creating weather chaos across multiple continents. Forest cover played a role too. During the cold snap, forests died back in many areas, replaced by tundra and grassland. Trees are darker than grassland, so they absorb more sunlight and warm the local climate. Losing forest cover meant losing another source of warming. But when temperatures recovered, forests expanded aggressively, their dark canopies absorbing sunlight and accelerating local warming. All these feedbacks interacted in complex ways, creating what climate scientists call tipping points, thresholds beyond which change becomes self-reinforcing and potentially irreversible. The scary part is we still don't fully understand where these tipping points are or what triggers them. The Younger Dryas proved that Earth's climate can flip between states incredibly quickly, faster than any gradual orbital forcing could explain. So how do we know all this? How can scientists reconstruct what happened 12,000 years ago with such detail? The answer lies in some of the most remarkable detective work in science. Multiple lines of evidence from completely different sources that all tell parts of the same story. Ice cores are the gold standard. Scientists have drilled into the ice sheets of Greenland and Antarctica, extracting cylinders of ice that preserve a detailed record of Earth's climate, going back hundreds of thousands of years. Each year's snowfall creates a distinct layer. By counting these layers, scientists can establish precise chronologies. By analysing the ice itself, they can determine past temperatures. Bubbles trapped in the ice contain actual samples of ancient atmosphere, showing greenhouse gas concentrations. Dust and volcanic ash layers mark specific events. The ice core from Greenland shows the Younger Dryas in stark detail, temperatures plunging by 15 degrees Celsius in less than a decade, atmospheric methane crashing, dust concentration spiking as vegetation died back, and winds stripped exposed soil. Then, 200 years later, temperatures rocketing back up even faster, possibly recovering half the cooling in less than 3 years. Sediment cores tell a different part of the story. Lakes and ocean basins accumulate layers of sediment year after year, each layer containing pollen, microscopic organisms, chemical signatures, and sometimes larger remains. These cores reveal how ecosystems responded to climate changes. During the Younger Dryas, pollen records show temperate forests in Europe being replaced by Arctic tundra within decades. Pine trees that had been advancing north suddenly disappeared from the record, replaced by dwarf willows and grasses. Marine sediment cores show how ocean circulation changed. The ratio of different oxygen isotopes in the shells of tiny sea creatures indicates water temperature and salinity. These proxies reveal exactly when the North Atlantic circulation collapsed and when it restarted. They show where fresh water flooded into the ocean and how quickly it spread. Cave formations, stalagmites and stalactites preserve another record. They grow continuously from dripping water, and their chemical composition reflects rainfall patterns and temperature. Some caves in China have stalagmites that grew throughout the entire Ice Age and into modern times. The chemical layers in these formations show how Asian monsoon patterns shifted during the Younger Dryas, proving the climate disruption wasn't just regional but global. Ancient DNA adds yet another dimension. Preserved in permafrost, sediments, and even the guts of frozen animals, DNA reveals which species lived where and when. It shows migration patterns, population crashes, and even diet changes. DNA from mammoth remains shows that their populations were already declining before the Younger Dryas, probably due to earlier climate warming, but that the cold snap and subsequent rapid warming delivered the final blow. Tree rings provide annual resolution for more recent parts of the record. Ancient logs preserved in bogs and lakes show growth patterns that reflect year-to-year climate variations. During the Younger Dryas, these trees show growth rates crashing. Right after it ended, growth explodes, trees adding centimetres of wood per year instead of millimetres. Archaeological evidence shows how humans responded. Settlement patterns changed dramatically. In the Middle East, people who had been living as mobile hunter-gatherers began settling into permanent villages right at the end of the Younger Dryas. The stress of rapid climate change might have pushed them toward agriculture as wild food sources became less reliable. In North America, the distinctive Clovis culture, known for their beautifully crafted spear points, disappeared at the Younger Dryas boundary, replaced by different cultural traditions with different technologies. Put all these lines of evidence together, and you get a detailed picture of the transition from the Ice Age to our modern world. But it's not a smooth transition. It's chaotic, violent, marked by rapid flips between climate states, and the most dramatic changes were still ahead. Because once the Younger Dryas ended, around 11,700 years ago, the warming didn't just resume, it accelerated. The feedback loops that had been held in check during the cold snap suddenly kicked in all at once. Ice sheets that had stabilised during the Younger Dryas began collapsing at unprecedented rates. Permafrost that had refrozen started thawing explosively. Ocean circulation that had weakened roared back to life. The world was about to transform faster than at any time in the previous 100,000 years. And standing in the path of that transformation were the massive ice sheets themselves, now unstable, fracturing and preparing to release floods that would dwarf anything in human memory. The real catastrophe was about to begin. The ice was melting, and when billions of tons of frozen water start moving, they don't move gently. Around 14,000 years ago, as temperatures began their relentless climb out of the glacial maximum, the great ice sheets that had dominated the northern hemisphere for 100,000 years started to collapse. Not gradually, not predictably, but in catastrophic bursts that would reshape entire continents and drown the world humanity had known. The first thing you need to understand is the scale. We're not talking about ice cubes melting in a glass. We're talking about ice sheets 2 miles thick covering areas the size of continents. The Laurentide ice sheet alone stretched from the Arctic Ocean to what's now New York City, from the Atlantic to the Rocky Mountains. It contained enough frozen water to raise global sea levels by 200 feet, and it was coming apart. But the water couldn't just flow away. The ice sheets had created a problem for themselves. As they grew, they had scoured the landscape beneath them, carving enormous basins and valleys. They had blocked river drainage patterns that had existed for millions of years. And as they melted, all that meltwater had nowhere to go. It pooled, it accumulated, it formed lakes of truly mind-boggling dimensions, trapped behind walls of ice that were themselves slowly disintegrating. The largest of these was Glacial Lake Agassiz. If you took all 5 Great Lakes and combined them, you'd have something less than half the size of Agassiz at its maximum extent. This single lake covered parts of what are now Manitoba, Ontario, Saskatchewan, North Dakota and Minnesota. It was 700 miles long, 250 miles wide in places, and in some spots over 2,000 feet deep. It contained more fresh water than all the lakes on Earth combined today, and it was held in place by a dam made of ice. Think about that for a moment. A body of water larger than the Black Sea, restrained only by frozen barriers that were actively melting in the warming climate. The ice dam didn't need to melt completely. It just needed to develop a crack, a weak spot, one breach that would allow the pressure behind it to do the rest. Around 13,000 years ago, somewhere along the southern margin of the ice sheet, that breach occurred. What happened next was apocalyptic. The initial failure would have been sudden, probably triggered by a particularly warm summer or a seismic event from the rebounding continental crust. Once the breach formed, the pressure of billions of gallons of water behind it would have widened the gap in minutes. Within hours, a relatively small leak would have become a torrent carrying ice blocks the size of houses. Within days, the entire southern section of the ice dam collapsed. Lake Agassiz didn't drain, it exploded. Water roared out of the breach at volumes that dwarf anything in modern experience. The Mississippi River, one of the largest rivers on Earth, moves about 600,000 cubic feet of water per second. During the peak of the Agassiz outburst, water was flowing at rates estimated between 15 and 30 million cubic feet per second. That's 25 to 50 times the volume of all the rivers on Earth combined, concentrated into a few catastrophic weeks. The floodwaters carved new channels hundreds of feet deep through solid bedrock. They carried boulders the size of buses for hundreds of miles. They stripped away topsoil that had taken thousands of years to form, leaving behind the scoured, lake-dotted landscape of the Canadian Shield that exists today. Any human settlements in the path of this deluge were simply erased. No warning, no time to escape, just a wall of water and ice moving faster than a person could run, obliterating everything in its path. But the destruction wasn't limited to the immediate flood zone. All that fresh water had to go somewhere. Much of it flowed south down the Mississippi Valley and into the Gulf of Mexico. But other outbursts at different times drained east through the Great Lakes and down the St. Lawrence or north into the Arctic Ocean. Each time, billions of gallons of fresh meltwater dumped into the ocean in geological instants. And this was just one lake. Across the northern hemisphere, dozens of similar ice dam lakes were forming, filling, and catastrophically draining. Each one represented a potential disaster. In the Pacific Northwest, an even more dramatic series of floods was remaking the landscape. Glacial Lake Missoula, though smaller than Agassiz, was positioned in a way that made its outburst uniquely destructive. The lake formed in what's now western Montana, dammed by a finger of the Cordilleran ice sheet that pushed south from Canada into Idaho. As the climate warmed, this ice dam would fail, the lake would drain catastrophically, then the ice would advance again, the lake would refill, and the whole cycle would repeat. This happened at least 40 times over the course of 3,000 years. Each Missoula flood released about 500 cubic miles of water in a matter of days. The floodwaters funneled through narrow mountain valleys, accelerating to speeds of 60 miles per hour. When they hit the relatively flat Columbia Basin in eastern Washington, they spread out across 3,000 square miles, creating a temporary inland sea hundreds of feet deep that drained in less than a week. The power of these floods was incomprehensible. They ripped 1,000-foot deep gorges through solid basalt. They created waterfalls 3 times the height of Niagara Falls that existed for days and then vanished. They carved enormous amphitheatre-shaped valleys called coulees, features so massive that early geologists couldn't understand what could have formed them. They transported house-sized boulders hundreds of miles from their sources. They left behind bizarre erosional features called the channeled scablands, a landscape so unique that it looks like something from another planet. For any humans living in the region, each flood would have been a civilization-ending event. Imagine seeing the horizon darken with an approaching wall of water, 400 feet high, moving at the speed of a galloping horse, carrying ice and rock and uprooted forests. There would be no high ground to reach, no way to outrun it, nowhere to hide. Communities that had existed for generations would simply cease to exist. Their only trace perhaps a few scattered stone tools found centuries later in flood deposits. But these dramatic outburst floods were only part of the story. They were catastrophic but relatively brief. The real transformation was happening more slowly but far more permanently. The seas were rising. As the ice sheets melted, they returned water to the oceans that had been locked away on land for 100,000 years. This wasn't a steady, gradual process. The rate of sea level rise varied dramatically depending on how fast the ice was melting. But the overall trend was relentless and unstoppable. Between 20,000 years ago and 8,000 years ago, global sea levels rose approximately 400 feet. That's a 40-story building's worth of vertical rise. 400 feet doesn't sound like much when you say it quickly, but think about what it means. Every low-lying coastal area, every river valley within hundreds of miles of the ocean, every island or peninsula that wasn't high and steep, all of it went underwater. And the flooding didn't happen all at once. It happened slowly enough that each generation might only see a few feet of change, but fast enough that within a few human lifetimes the landscape of childhood would be completely unrecognizable. For the human populations living through this, it must have seemed like the world was ending in slow motion. The best hunting grounds, the richest fishing areas, the most productive gathering sites were all along coasts and rivers. These were the areas that flooded first. Generation after generation, communities would be forced to move inland, to abandon settlements that had been occupied for centuries, to learn new survival strategies in less productive territories. Nowhere were these losses more dramatic than in the places that simply ceased to exist as land at all. Doggerland is one of the great lost places of human prehistory. For most of the last ice age, what's now the North Sea between Britain and continental Europe was dry land. Not marginal tundra, but rich, productive territory. River valleys, wetlands, rolling hills, forests. Archaeological evidence suggests it was one of the most densely populated regions in Mesolithic Europe. Doggerland was the heart of the Ice Age world in northern Europe. Rivers that now drain separately into the North Sea, the Thames, the Rhine, the Seine, all flow together across Doggerland into a single massive river system that emptied into the Atlantic far to the north. The shallow seas that surrounded it were probably incredibly productive fishing grounds. The land itself supported herds of aurochs, red deer, and wild horses. For the humans who lived there, it was prime real estate. Then the seas began to rise. Initially, the changes would have been subtle. The coastal fishing areas moved slightly inland. Islands appeared where there had been continuous land. River mouths shifted. But by 10,000 years ago, Doggerland was shrinking noticeably. What had been rolling hills became islands. River valleys became straits. Communities that had been inland suddenly found themselves on narrowing coastlines. By 8,000 years ago, Doggerland was reduced to a few large islands. Archaeological sites from this period showed desperate adaptation strategies. People shifted to more maritime lifestyles, developing sophisticated boat technology and focusing on fishing and sea mammal hunting. But they were fighting a losing battle against the rising water. Around 6,200 years ago, Doggerland may have suffered its final catastrophe. Geological evidence suggests a massive underwater landslide off the coast of Norway. The Storegga slide triggered a tsunami that would have been devastating to the remaining low-lying islands. Any communities that had managed to hang on despite the rising seas would have been swept away in hours. Within a few generations after that, the last remnants of Doggerland slipped beneath the waves permanently. Britain became an island. The North Sea reached its modern extent, and an entire landscape that had been home to thousands of people for tens of thousands of years existed only in the sediments of the sea floor. We know about Doggerland now only because fishing trawlers occasionally bring up artefacts from what were once dry land sites, mammoth teeth, stone tools, pieces of worked wood, evidence of a lost world. The same process was happening around the globe. Beringia, the vast landmass that had connected Asia and North America during the Ice Age, was slowly drowning. At its maximum extent, Beringia had been over 1,000 miles wide from north to south. enormous plain that stretched from Siberia to Alaska. The people who first colonized the Americas had walked across this land, following herds of mammoth and bison. As sea levels rose, Beringia shrank. The first areas to flood were the southern coasts, cutting off the easiest migration routes. Then the centre of the landmass began to flood, creating an inland sea that eventually connected to the ocean. By 11,000 years ago, only a narrow bridge of land remained. By 10,000 years ago, that too was gone. The Bering Strait opened, and for the first time in 100,000 years, the continents of Asia and North America were completely separated. This had enormous consequences for the human populations on both sides. Groups that had maintained contact for thousands of years were suddenly isolated by 50 miles of ocean. The genetic and cultural exchange that had characterized human populations throughout the Ice Age came to an abrupt end. The peoples of the Americas and the peoples of Asia began diverging along separate evolutionary and cultural paths, all because the ice had melted and the seas had risen. But perhaps nowhere is the human impact of rising seas more potentially dramatic than in the Black Sea. Today, the Black Sea is connected to the Mediterranean through the narrow Bosphorus Strait. But for most of the Ice Age, when sea levels were hundreds of feet lower, the Black Sea was an isolated freshwater lake. Its level was controlled by the rivers that flowed into it, and it sat about 500 feet lower than the Mediterranean. As global sea levels rose with the melting ice sheets, the Mediterranean crept higher and higher. Around 7,600 years ago, according to the Black Sea deluge hypothesis proposed by geologists Walter Pittman and William Ryan, the rising Mediterranean finally topped the natural barrier at the Bosphorus. What happened next was a flood that might have inspired some of humanity's oldest and most persistent myths. Seawater began cascading into the lower Black Sea basin, not gradually, but as a waterfall that would have dwarfed anything in the modern world. Calculations suggest water was pouring through the breach at rates 200 times the flow of Niagara Falls, creating a roar that could be heard for hundreds of miles. The Black Sea's level was rising over 6 inches per day. Coastlines were advancing inland by a mile or more per day in the flattest areas. Any human communities around the Black Sea would have had no way to understand what was happening. This wasn't a seasonal flood that would recede. This was the ocean itself, permanently reclaiming land, advancing relentlessly day after day, week after week. Settlements, fields, fishing camps, hunting grounds, all drowning beneath salt water that killed the freshwater ecosystems they depended on. The flooding continued for at least a year, possibly several years, until the Black Sea reached its modern level. In that time, over 60,000 square miles of land, an area the size of Georgia, vanished beneath the waves. Archaeological evidence from the region shows a sudden abandonment of settlements around this time, with populations migrating outward into surrounding regions. Some researchers think the Black Sea deluge was so catastrophic, so beyond normal human experience, that it became encoded in the mythology of every culture around the region. The Epic of Gilgamesh, the biblical Noah story, the Greek legend of Deucalion's flood, these might all be distant cultural memories of the day the sea broke through and drowned the world. Whether or not the deluge hypothesis is correct in every detail, the broader reality is undeniable. Around the world, coastal populations were experiencing ongoing catastrophic loss of land to rising seas, and unlike modern sea level rise, which we can measure in millimetres per year, late glacial sea level rise was dramatic enough to be visible within a single human lifetime. Imagine being a child, playing on beaches and fishing in estuaries that you could walk to from your settlement. By the time you're middle-aged, those beaches are a half-day's walk away, and the old camping grounds are underwater. By the time your grandchildren are born, the places you knew as a child exist only in stories. That cycle repeated dozens of times over thousands of years, each generation forced to adapt to a literally shrinking world. The psychological impact must have been profound. Every culture that survived this period would have developed flood myths, Stories of a time when the waters rose and the old world drowned. These weren't fantasies or religious allegories. They were cultural memory, encoded in story form of actual events that had shaped human history. But the floods and rising seas did more than just displace people and drown landscapes. They fundamentally altered Earth's climate system in ways that would trigger one final crisis before the Ice Age fully released its grip. All that meltwater pouring into the oceans wasn't just raising sea levels, it was changing ocean circulation patterns. The North Atlantic, in particular, operates like a giant conveyor belt. Warm surface water flows north from the tropics, bringing heat to northern Europe. When it reaches the Arctic, it cools, becomes denser, and sinks, returning south as a deep current. This system, called the Atlantic Meridional Overturning Circulation, is responsible for keeping northern Europe much warmer than it would otherwise be. But the system depends on salt water. Fresh water is less dense than salt water and won't sink the same way. When billions of gallons of fresh meltwater from Lake Agassiz and other glacial lakes poured into the North Atlantic, they created a lens of fresh water that disrupted the entire circulation system. The conveyor belt slowed down. Some researchers think it may have stopped entirely for a period. The result was a climate disaster called the Younger Dryas. Around 12 to 900 years ago, just as the world was warming and the ice was retreating, temperatures in the northern hemisphere suddenly plunged back toward full glacial conditions. Ice sheets that had been melting began advancing again. Forests that had started to recolonize formerly glaciated regions were replaced by tundra. The warming trend that had defined the previous 2,000 years reversed in less than a decade. This wasn't a local cold snap. It was a return to Ice Age conditions that lasted 1,200 years. And it happened because the melting ice had disrupted the very climate systems that were ending the Ice Age. The planet had entered a feedback loop, where warming caused melting, which caused cooling, which slowed the melting, which eventually allowed warming to resume. The climate system was drunk, lurching between states, unable to find equilibrium. For human populations, the Younger Dryas was devastating. Groups that had adapted to warming conditions, expanding into newly habitable territories, following migrating animal herds north, suddenly found their food sources disappearing and the cold returning. Archaeological evidence shows widespread settlement abandonment and population crashes during this period. Some researchers think the stress of the Younger Dryas may have been the final push that drove human populations in the Fertile Crescent to develop agriculture. When you can't rely on wild resources anymore, you have to start producing your own food. Around 11,700 years ago, the Younger Dryas ended as abruptly as it had begun. The meltwater pulses that had disrupted ocean circulation finally stopped. The conveyor belt restarted. Temperatures shot back up, even faster than they had dropped. The ice sheets began their final retreat. The long, unstable transition out of the Ice Age was finally over, but the damage was done. Entire landscapes had been reshaped. Coastlines had moved hundreds of miles inland. Freshwater systems had been completely reorganized, and human populations had been pushed, displaced, and forced to adapt more radically in 5,000 years than they had in the previous 50,000, utterly transformed. And humanity, tested yet again by catastrophic environmental change, had once more found a way to survive. But survival always comes with a cost, and the cost of surviving the Great Melt would shape human civilization in ways we're still discovering today. Between 15,000 and 10,000 years ago, something unprecedented happened on Earth. Not a meteor strike, not a supervolcano, not even a sudden climate catastrophe in the traditional sense. It was something quieter, but ultimately more devastating. The planet lost its giants. We're talking about an extinction event that wiped out roughly 178 species of large mammals, animals that had dominated their ecosystems for hundreds of thousands, sometimes millions of years. Woolly mammoths that had survived multiple ice ages, mastodons that had ranged across North America since the Miocene, giant ground sloths the size of elephants. saber-toothed cats that had perfected ambush hunting over millennia, cave lions larger than any big cat alive today, dire wolves, giant beavers the size of bears, short-faced bears that stood 12 feet tall on their hind legs, all gone. Not gradually over millions of years, which is how extinction usually works, but in a geological eye blink. 5,000 years. That's nothing in evolutionary time. It's barely 200 human generations. To understand just how catastrophic this was, you need to appreciate what the world looked like before the extinctions began. During the last glacial maximum megafauna, animals, over 100 pounds, dominated every continent except Antarctica. North America alone had over 50 species of large mammals, mammoths and mastodons browsing in mixed herds, 3 species of ground sloths, each adapted to different ecological niches, 2 species of saber-toothed cats competing with dire wolves, American lions and short-faced bears for prey, glyptodonts, armoured mammals that looked like Volkswagen Beetles with tails, giant camels, ancient horses, massive bison species that made modern buffalo look small. South America was even more spectacular. The continent had been isolated for millions of years, developing its own unique megafauna. Ground sloths that weighed 8,000 pounds, toxodon, rhinoceros-like herbivores with hippo bodies and rodent teeth, macrauchenia, bizarre mammals with elephant-like trunks and camel-like bodies, saber-toothed marsupials that had evolved predatory lifestyles completely independently from their placental counterparts in North America, terror birds, 10-foot-tall flightless predators with beaks that could crush bone. Eurasia had its own giants, woolly rhinos ranging from Spain to Siberia, cave bears that hibernated in massive underground chambers, Megaloceros, the Irish elk with antlers spanning 12 feet, steppe bison, European lions, all the charismatic megafauna we associate with Ice Age cave paintings, thriving populations that seemed indestructible. Australia's megafauna were perhaps the strangest of all. Diprotodon, the largest marsupial that ever lived, a 3-ton wombat relative, giant kangaroos that stood 10 feet tall and couldn't hop, Megalania, a land-dwelling monitor lizard 20 feet long, marsupial lions with retractable thumb claws for ripping flesh, thunderbirds, massive flightless fowl with massive beaks. Then the ice sheet started melting and everything changed. Within 5,000 years, 75% of North American megafauna genera were gone, 80% in South America, around 70% in Australia, which actually started losing species earlier than other continents. Even Eurasia, which fared better than most regions, lost roughly half its large mammal species. The question that has obsessed scientists for over a century is simple to ask but devilishly difficult to answer. Why? The first theory, and still the most obvious, is climate change. The end of the Ice Age wasn't just about melting glaciers and rising seas. It fundamentally restructured every ecosystem on the planet. Habitats that had been stable for tens of thousands of years disappeared in centuries. The Mammoth Steppe, that vast grassland ecosystem that stretched from Spain to Canada, covering more land area than any biome on Earth today, it vanished. As temperatures rose and precipitation patterns shifted, the unique combination of grasses, forbs and shrubs that sustained mammoth herds couldn't survive. This wasn't just warming, it was habitat transformation on a continental scale. The vegetation that replaced the Mammoth Steppe, birch forests, wetlands, tundra, provided far less nutrition for grazing megafauna. Mammoths needed to consume roughly 400 pounds of vegetation daily. The grasses of the Mammoth Steppe were nutrient-dense enough to support that metabolism. The replacement vegetation wasn't. You can see this pattern repeated across ecosystems. In North America, the spruce forest that had dominated the continent's interior during glacial times gave way to deciduous hardwoods. Mastodons, specialised browsers that fed on spruce and pine suddenly found their preferred food disappearing. The mosaic of grasslands and parklands that had supported diverse grazing herds fragmented into smaller patches, separated by thick forest that large animals couldn't easily traverse. In northern Europe, the open tundra steppe that had supported mammoth, woolly rhino and reindeer populations gave way to dense boreal forests. These forests provided cover for smaller prey species like deer and elk, but they couldn't support the mega-herbivore populations that had thrived in open country. But here's the thing, megafauna had survived climate changes before. The Pleistocene was characterised by repeated glacial cycles. Every 100,000 years or so, ice sheets advanced and retreated. Temperatures swung wildly. Sea levels rose and fell by hundreds of feet. Ecosystems transformed repeatedly. Yet the megafauna made it through all those previous transitions. Mammoths, for instance, had survived at least 4 full glacial cycles before finally going extinct. Why did this particular warming event prove fatal? That question led scientists to the second major theory. Humans, not climate change, but hunting pressure from an increasingly sophisticated and rapidly expanding population of Homo sapiens. This hypothesis, sometimes called the overkill theory, argues that human hunters, not environmental change, drove the extinction wave. The evidence for human involvement is compelling. First, there's the timing. The extinction wave doesn't correlate perfectly with climate change. It correlates with human arrival. In Australia, megafauna started disappearing around 45,000 years ago, shortly after humans first colonised the continent. In North America, extinctions accelerated dramatically between 13,000 and 11,000 years ago, right when Clovis culture hunters were spreading across the continent. In Madagascar, giant lemurs and elephant birds survived until just 2,000 years ago. They disappeared within centuries of human arrival. New Zealand's moa, massive flightless birds, lasted until 1300 CE. Then Polynesian settlers arrived, and within 200 years all moa species were extinct. This pattern, extinct shortly after humans arrive, shows up again and again. Continental islands like Cyprus lost their dwarf hippos and elephants soon after humans settled there. Remote Pacific islands lost dozens of bird species when Polynesian voyagers reached them. The Caribbean lost its unique ground sloths when humans colonised those islands. The archaeological evidence supports this connection. Clovis kill sites in North America show sophisticated hunting strategies. Drive lines where hunters channeled mammoths into swamps or box canyons. Ambush sites at river crossings, evidence of systematic butchering, with hunters taking the choicest cuts and leaving the rest. And it wasn't just opportunistic scavenging. Chemical analysis of Clovis points shows they were specifically engineered for penetrating thick hide. The fluting, those distinctive grooves running up the centre of Clovis spear points, reduced weight while maintaining strength, creating projectiles that could be thrown with deadly accuracy at large, dangerous prey. Human hunting technology was improving rapidly during this period. Spear throwers, atlatls, that could launch projectiles with 3 times the force of hand-thrown spears. Composite weapons combining different materials for optimal performance. Coordinated group hunting tactics that allowed small bands to take down animals many times their size. Computer models of human hunting impacts support the overkill hypothesis. Simulations show that even very modest hunting pressure, 1 megafauna animal killed per person per year, could drive large mammal populations to extinction in just a few centuries. This is especially true for animals with slow reproductive rates. Mammoths didn't reach sexual maturity until around age 15 and had gestation periods of 22 months. They might produce only 5 or 6 offspring in a lifetime. You didn't need to kill many mammoths to prevent population recovery. And it's not just about direct hunting. Human activity transformed landscapes in ways that made survival harder for megafauna. Indigenous peoples across the Americas, Australia and other regions used fire as a landscape management tool. Regular burning created patchwork mosaics of different vegetation types. favouring certain game animals while disadvantaging others. These human-altered ecosystems might have been less suitable for megafauna that had evolved for different habitat configurations, but the climate versus human debate isn't really either-or. The third theory, and the one most scientists now favour, is that it was both. A perfect storm where climate stress weakened megafauna populations that were then finished off by human hunting pressure. Neither force alone would have been sufficient, but combined, they were devastating. Think about it from a mammoth's perspective. You're dealing with rapidly changing vegetation patterns. Your preferred grasses are disappearing, replaced by less nutritious plants. Your population is under stress, reproduction rates declining, juvenile survival dropping. Then humans arrive. Not many at first, just a few bands of highly efficient hunters who have spent millennia perfecting techniques for killing large, dangerous prey. Under normal conditions, your population could absorb some hunting losses, but these aren't normal conditions. You're already struggling with climate-induced food stress. Every mammoth that hunters kill is one that can't reproduce, one that can't help raise the next generation. The combination proves fatal. Within a few centuries, your populations fragment, then collapse, then disappear entirely. This perfect storm theory explains several puzzling features of the extinction wave. It explains why extinctions correlate with both climate change and human arrival. Both factors were necessary. It explains why some regions lost more species than others. The severity depended on how much climate disruption occurred and how intensively humans hunted. It explains why smaller animals largely survived while megafauna disappeared. Small species reproduce faster and recover more quickly from hunting pressure. Look at the extinction patterns across continents, and this dual pressure hypothesis makes even more sense. Africa and parts of Asia, where humans and megafauna had co-evolved for millions of years, lost relatively few species. African elephants, rhinos, hippos, giraffes all survived despite living alongside human hunters throughout their evolutionary history. These animals had evolved behavioural adaptations that made them harder to hunt. Wariness of human presence, rapid flight responses, dangerous defensive behaviours. But in the Americas, Australia, and remote islands where megafauna encountered humans for the first time, extinctions were catastrophic. These animals had no evolutionary experience with human hunters, no instinctive fear responses, no defensive behaviours calibrated to threat from bipedal predators with long-range weapons. A mammoth that had survived encounters with saber-toothed cats and short-faced bears by standing its ground and using its tusks defensively might face down human hunters the same way. Fatal mistake. Humans could kill from a distance, using coordinated tactics that no previous predator had employed. The naive prey hypothesis helps explain why extinctions were so rapid in regions where humans were newcomers. Animals that don't recognize humans as threats are easy to hunt. By the time defensive behaviors could evolve through natural selection, populations were already crashing. But the extinctions weren't just about losing individual species. They triggered cascading ecosystem collapses that transformed entire landscapes. Megafauna weren't just big animals, they were ecosystem engineers, species whose presence fundamentally shaped the environment around them. Consider mammoths. A single mammoth herd could consume 10 tons of vegetation daily. But they weren't just eating. They were pruning, trampling and fertilizing. Mammoths kept forests from encroaching on grasslands by knocking down saplings. They spread seeds through their dung, sometimes moving them hundreds of miles. Their feeding behaviour created patchy, diverse landscapes that supported countless other species. When mammoths disappeared, those ecosystem services vanished too. Without large herbivores controlling tree growth, the mammoth steppe transformed into forest and tundra. Species adapted to open grasslands found themselves without habitat. The productive, diverse ecosystem that had supported the richest megafauna communities in Earth's history collapsed into simpler, less diverse systems. Ground sloths in South America played similar roles. Giant species created extensive cave systems through their excavation behaviours. Multiple other species used these caves for shelter. Ground sloths were also major seed dispersers for certain tree species. Some plants, like the avocado, evolved large fruits specifically to be eaten and dispersed by megafauna. When the ground sloths disappeared, these plants lost their primary seed dispersal agents. Today, avocados and several other large-fruited trees are considered evolutionary anachronisms, plants still producing fruits for animals that no longer exist. Mastodons in North American forests created and maintained openings in dense woodland, generating habitat mosaics that supported diverse plant and animal communities. Without mastodons, forests became denser and more uniform, less suitable for species that needed varied habitat types. The extinction of megafaunal predators had equally profound effects. Saber-toothed cats and other large carnivores had kept herbivore populations in check. When the top predators disappeared, whatever herbivores remained experienced release from predation pressure. But this wasn't necessarily good for them. Without predators selecting out weak and sick individuals, disease became more prevalent in herbivore populations. Fire regimes changed too. Megafauna grazing had kept fuel loads low in many ecosystems. When those large grazers disappeared, dead vegetation accumulated. Some researchers think this contributed to increased fire frequency in certain regions, further transforming habitats. Even nutrient cycling shifted. The bodies of megafauna represented massive pools of nutrients. When they died, whether from natural causes or predation, those nutrients were redistributed across landscapes. Predators carried nutrients from kill sites to distant dens. Scavengers spread them further. The loss of megafauna meant less nutrient redistribution, potentially impoverishing soils in some regions. But some species survived, and understanding why reveals important lessons about extinction resilience. The survivors shared certain characteristics that the extinct species lacked. Reproductive flexibility. Deer, elk, and caribou can adjust their reproductive rates based on environmental conditions. Good years, they produce more offspring. Bad years, they cut back. Megafauna with rigid, slow reproductive cycles couldn't make these adjustments. Dietary generalization. Bison survived in North America partly because they could eat a wider variety of plants than more specialized grazers. When preferred foods disappeared, bison switched to alternatives. Specialized feeders like mammoths and mastodons had fewer options. Behavioral adaptability. Species that could quickly modify their behavior in response to new threats had better survival odds. Elk and deer learned to avoid human hunters. They shifted to nocturnal activity patterns in areas with heavy hunting pressure. They developed extreme wariness of human presence. Smaller body size. Almost universally, smaller species within animal groups survived better than their larger relatives. Large body size, which had been advantageous during stable ice age conditions, became a liability. Large animals needed more food, had longer generation times, and made more attractive hunting targets. Habitat flexibility. Species that could thrive in multiple habitat types had refuges when their preferred environments transformed. Specialists tied to particular habitat configurations had nowhere to go when those habitats disappeared. These survival factors weren't distributed evenly across continents, which partly explains regional variation in extinction severity. Africa, with its long history of human megafauna coexistence, had selected for many of these survival traits over millions of years. American and Australian megafauna, encountering sophisticated human hunters for the first time, lacked these evolutionary refinements. The lessons from this ancient extinction wave resonate powerfully today. We're living through another period of rapid climate change and expanding human impacts. The sixth extinction, as conservation biologists call it, is already underway. Current extinction rates are estimated at 100 to 1,000 times higher than background rates. The parallels are striking. Like 12,000 years ago, we're seeing climate-driven habitat transformation happening faster than many species can adapt. Like then, we're seeing human activities, habitat destruction, hunting, pollution, creating additional stress on already vulnerable populations. And like then, we're discovering that the combination of pressures is far more devastating than either force alone. The megafauna extinctions taught us that even species that seem invincible, animals that had survived for millions of years through multiple climate cycles, can collapse rapidly when pushed beyond their adaptive limits. They showed us that loss of keystone species triggers cascading effects throughout ecosystems, changes that persist for thousands of years. They demonstrated that naive prey, species without evolutionary experience of particular threats, are especially vulnerable. Today's endangered species, confined to shrinking habitats and encountering novel threats like climate change, habitat fragmentation, and emerging diseases, might be similarly naive, lacking the evolutionary preparation to respond effectively. But there's one crucial difference between then and now. The humans who contributed to megafauna extinctions 12,000 years ago didn't understand what they were doing. They couldn't have predicted that their hunting would eliminate entire species, or that those extinctions would transform ecosystems. They were just trying to survive. We don't have that excuse. We understand the consequences of our actions. We can see extinctions happening in real time. We have the knowledge and potentially the tools to prevent further losses. The question is whether we'll apply those lessons before we lose the elephants, rhinos, and other modern megafauna that are the last survivors of what was once a world of giants. The extinction wave that swept the planet 12,000 years ago wasn't inevitable. It was the result of specific, understandable pressures that happened to align at a particular moment in history. Today we're creating similar alignments. Rapid climate change plus intense human pressure equals extinction risk. The difference is, this time we get to choose how the story ends. The ice was melting, and with it, the world humans had known for 100,000 years was disappearing. For Ice Age hunters, the apocalypse didn't arrive as a single catastrophic event. It came as a slow-motion collapse of everything their ancestors had perfected over thousands of generations. The mammoths were dying out, the giant bison herds were shrinking, the reindeer that had migrated predictably for millennia were changing their routes, following vegetation patterns that no longer made sense. Imagine being part of a hunting band around 14,000 years ago. Your grandfather's grandfather had hunted mammoth in these valleys. The techniques had been passed down through hundreds of generations. You knew where the herds would be in each season. You knew which mountain passes they'd use during migration. You'd practiced mammoth hunting tactics since you were old enough to hold a spear. Then suddenly, over the span of just a few generations, the mammoths weren't there anymore. Not because you'd overhunted them, though that was part of it, but because the landscape itself was transforming. The cold grasslands where mammoths thrived were becoming forests. The herds that remained were smaller, more scattered, harder to predict. This was an existential crisis. For 100,000 years, humans had been apex predators specializing in megafauna hunting. Large mammals provided everything: meat, fat, hides for clothing and shelter, bones for tools, sinew for bindings. A single mammoth could feed a band of 50 people for weeks. Losing access to these animals wasn't just inconvenient, it threatened the entire foundation of Ice Age survival strategies. But humans didn't starve. Instead, they did what the bottleneck had selected them for. They adapted. The archaeological record from this period shows something remarkable. A sudden explosion of dietary diversity. Sites that had previously contained almost exclusively large mammal bones suddenly show evidence of fishing, bird hunting, shellfish gathering, and intensive plant processing. This wasn't a gradual shift. It happened fast, within a few centuries at most. That's the blink of an eye in evolutionary terms. Let's look at what actually changed. First, fishing became systematic and sophisticated. During the Ice Age, humans had occasionally caught fish, but it wasn't a major food source. Too much effort for too little return when you could hunt megafauna instead. But as the ice melted and sea levels rose, coastal areas transformed. Estuaries formed where rivers met the advancing ocean. These brackish mixing zones became incredibly productive, teeming with fish, shellfish and waterfowl. Humans responded by developing fishing technologies that would have been unthinkable to their Ice Age ancestors. Sophisticated fish traps made from woven reeds that could be set in rivers and checked daily. Bonefish hooks in dozens of specialised designs, each optimised for different fish species. Harpoons with detachable heads and line attachments for taking large fish and sea mammals. Nets woven from plant fibres that allowed entire communities to harvest huge quantities of fish at once. Shell middens, massive piles of discarded shellfish remains, begin appearing at coastal sites around this time. Some of these middens are enormous, hundreds of feet long and dozens of feet deep, representing thousands of years of continuous shellfish harvesting. This tells us something profound. Humans weren't just supplementing their diet with shellfish during emergencies. They were making it a staple, a reliable food source that could be harvested year-round with minimal risk. The Utterbell culture in Scandinavia provides a perfect example. Around 12,000 years ago, as forest replaced tundra, these coastal peoples developed an entire way of life based on marine resources. Their sites show systematic exploitation of oysters, mussels, fish, seals, and waterfowl. They developed specialised tools for every task: oyster knives, fish scalers, bird snares, seal harpoons. They weren't primitive scavengers making do with whatever they could find. They were sophisticated marine resource managers with detailed knowledge of seasonal patterns and sustainable harvesting practices. But the most important shift was happening with plants. For millions of years, human ancestors had been primarily carnivorous. Plant foods were supplementary, something you ate when meat wasn't available. The Ice Age had reinforced this pattern. Cold climates meant fewer plant foods were available, and the ones that existed were often low in calories and difficult to process. The warming changed everything. As temperatures rose and rainfall increased, grasslands exploded with new plant growth. The ancestors of wheat and barley, wild grasses that had existed in small scattered populations, suddenly had ideal conditions. They spread rapidly across the Fertile Crescent, that arc of land stretching from the Persian Gulf through modern Iraq and Syria to the eastern Mediterranean. These wild cereals were nutritious but difficult to harvest. The seeds shattered easily when they ripened, scattering on the ground before humans could collect them. They were also small and required intensive processing, grinding to remove tough outer husks before they could be eaten. But humans figured it out. Archaeological sites from around 13,000 years ago show the first systematic cereal harvesting. Stone sickle blades with a characteristic polish from cutting grass stems. Grinding stones worn smooth from processing seeds. Storage pits lined with clay to keep harvested grain dry through the winter. This was revolutionary. For the first time in human history, people could store significant calories for later use. A single good harvest season could provide food for months. This changed the fundamental mathematics of survival. You no longer had to follow game animals constantly. You could stay in one place, at least for the part of the year, and live off stored grain. But early cereal harvesting had a problem. Wild wheat and barley had that shattering characteristic, evolved to spread their seeds naturally. It made them incredibly frustrating to harvest. You had to catch them at exactly the right moment, not too early when seeds weren't ripe, not too late when they'd already scattered. Then humans made a discovery that would change the course of civilization. Some individual wheat plants had a genetic mutation that made their seeds stay on the stalk when they ripened, instead of shattering. These mutants were actually disadvantaged in the wild because their seeds didn't disperse. But for humans trying to harvest grain, they were perfect. When humans preferentially harvested these non-shattering plants, collecting their seeds and scattering some near their camps for next year, they unknowingly began the world's first domestication program. Within a few thousand years, the wheat growing near human settlements was fundamentally different from wild varieties. Larger seeds, non-shattering stems, tougher stalks that didn't break in the wind. Humans had created a new organism, one that couldn't survive without human cultivation. The same process happened independently with barley in the Middle East, rice in China, and maize in Mexico. By 10,000 years ago, people in multiple regions had figured out agriculture. They were no longer just taking what nature provided. They were actively managing plant populations, selecting for desirable traits, creating landscapes that served human needs. Agriculture didn't develop because someone had a brilliant idea. It emerged from necessity as traditional food sources disappeared and populations had nowhere else to go. But once it existed, it unleashed consequences nobody could have predicted. The most immediate consequence was settlement. When you're hunting and gathering, you have to be mobile. Food sources are scattered across the landscape. You follow seasonal patterns, moving to where resources are available. Bands of 30 to 50 people was optimal, small enough to move quickly, large enough for effective hunting and defence. But agriculture changed the equation. If you've planted crops, you need to stay put to protect them from animals, to water them if needed, to harvest them at the right time. Storage of grain required permanent structures. Processing required heavy grinding stones that were impractical to transport. The first permanent settlements appeared around 12,000 years ago. Not cities yet, but villages, clusters of circular or oval houses made from stone, mud brick and timber. Each structure housed a single extended family. Villages contained 50 to 200 people, far larger than traditional hunter-gatherer bands. Jericho in the Jordan Valley provides our best early example. Around 11,000 years ago, this settlement contained perhaps 70 houses, supporting a population of 300 to 400 people. They were growing domesticated wheat and barley, but they were also still hunting wild gazelles and gathering wild plants. This wasn't full agriculture yet. It was something transitional, a mixed economy that combined farming with traditional food gathering. But Jericho had something unprecedented. Walls. Massive stone fortifications with towers reaching 20 feet high. Building them would have required thousands of person-hours of coordinated labour. This tells us something profound. The settlement was worth defending. People had invested too much in their fields, their houses, their storage facilities to simply abandon them when threatened. It also tells us that threats existed. Walls don't just appear. They're built in response to conflict. As the best agricultural lands attracted larger permanent populations, competition intensified. Groups that had once simply avoided each other by moving to different areas now found themselves fighting over specific locations that couldn't be easily replaced. Çatalhöyük, in modern Turkey, shows us where this process led. By 9,000 years ago, this settlement housed perhaps 8,000 people, making it one of the first true cities in human history. The architecture was extraordinary. Houses built wall to wall with no streets, accessed by ladders through roof openings. The entire settlement was essentially one continuous structure. Inside these houses we see the full emergence of agricultural society. Storage bins filled with grain, grinding stones worn concave from thousands of hours of use, sophisticated ovens for baking bread, toolkits that included sickles, hoes, grain processing equipment, and cooking implements far more diverse than anything from the Ice Age. But we also see something else. Differentiation. Some houses were larger and better constructed. Some burials contained valuable trade goods, obsidian from distant sources, seashells from the Mediterranean, copper ornaments. Other burials contained nothing but the body. Society was stratifying. Hierarchies were emerging. This wasn't accidental. Agriculture created something. Unprecedented storable surplus. During the Ice Age you could only eat what you could carry or consume immediately. There was no practical way to accumulate wealth. Everyone in a band had roughly the same material possessions, but with grain storage, some families could accumulate more than others. Maybe they had better land, maybe they worked harder, maybe they got lucky with weather conditions. Whatever the reason, inequality became possible, and once possible, it became inevitable. Some people began specializing. If you could trade stored grain for other goods, you didn't have to farm yourself. Archaeological evidence from early agricultural settlements shows craft specialists, potters, toolmakers, builders, traders. Each person focusing on what they did best, trading their products for food produced by others. This specialization drove technological innovation at unprecedented speed. Consider pottery. During the Ice Age, humans had occasionally made crude-fired clay objects, but pottery as a systematic technology didn't exist. It wasn't practical for mobile populations. Ceramic vessels are heavy and fragile, impractical to transport. But for settled agricultural communities, pottery was revolutionary. You could store grain in sealed vessels that protected it from moisture and pests. You could cook stews and porridges that made grain more digestible. You could ferment foods, creating new flavours and preservation methods. By 10,000 years ago, sophisticated pottery traditions had emerged across agricultural regions, each with distinctive styles and decorative patterns. Stone tool technology was transforming too. The chipped stone tools that had dominated for millions of years began giving way to polished stone implements. Axes that could fell trees efficiently, adzes for shaping wood, grinding stones for processing grain. These polished tools took far longer to make than simple flaked implements, but they were more durable and effective. You could invest weeks in creating a perfect stone axe because you weren't moving every few weeks. The bow and arrow, probably invented during this period, revolutionized hunting. Spears had been humanity's primary hunting weapon for hundreds of thousands of years. They were effective but limited in range and required significant strength to use. Bows allowed hunters to take game at much greater distances with less physical power required. A skilled archer could harvest birds and small mammals that would have been nearly impossible to hunt with spears. But perhaps the most important technological innovation was something we can barely see in the archaeological record: plant and animal domestication expertise. Early farmers were conducting sophisticated multi-generational breeding programs. They were observing which plants produced the most seeds, which grew fastest, which were most resistant to disease. They were selecting breeding stock based on complex criteria, creating varieties optimized for human needs. The same process was happening with animals. Dogs had been domesticated during the Ice Age, probably as hunting companions and camp guards. But after the ice melted, humans began domesticating sheep, goats, pigs, and cattle. By 10,000 years ago, mixed farming combining crops and livestock had become established across the Fertile Crescent. Domesticated animals provided multiple benefits: meat, milk, wool, leather, and labour for pulling ploughs and transporting goods. They were living storage systems that could convert plant materials humans couldn't eat into forms we could, while simultaneously reproducing themselves. All of this created something unprecedented: demographic expansion. Hunter-gatherer populations had been limited by food availability and mobility constraints. Women in mobile bands typically spaced children about 4 years apart because carrying multiple small children while travelling was impractical. Population growth was slow, maybe 0.01% per year. But agricultural communities could support larger families. Settled life meant women could have children more frequently. Grain-based porridges made weaning easier. Greater food security meant more children survived to adulthood. Agricultural populations grew at perhaps 0.1% annually, 100 times faster than hunter-gatherers. This doesn't sound like much, but compound growth is powerful. At 0.1% annual growth, a population doubles every 700 years. Within a few thousand years, agricultural populations vastly outnumbered remaining hunter-gatherers. By 8,000 years ago, The majority of people in the Middle East, parts of China, and the Americas were farmers. But population growth created new pressures. The best agricultural lands filled up. Families needed to find new fields for younger generations. This drove expansion. Farming communities spread from the Fertile Crescent into Europe, North Africa, and Central Asia. Separate agricultural centres in China, Sub-Saharan Africa, and the Americas underwent similar expansions. This expansion often came at the expense of remaining hunter-gatherers. When farmers moved into new territories, they brought not just agriculture, but also diseases. Dense settled populations living in close contact with domesticated animals created ideal conditions for epidemic diseases, measles, smallpox, tuberculosis, and others. These diseases ravaged hunter-gatherer populations that had no immunity. Archaeological evidence from Europe shows this process clearly. As farmers from the Middle East expanded into Europe starting around 9,000 years ago, the genetic signatures of indigenous European hunter-gatherers largely disappeared. They were replaced, outcompeted, or absorbed by incoming agricultural populations. The same pattern played out globally wherever farmers encountered hunter-gatherers. But agricultural expansion also drove social complexity. Managing irrigation systems required coordination among multiple families. Defending stored grain from raiders required organised military forces. Resolving disputes about land ownership required authorities and rules. Simple egalitarian bands evolved into tribes, then chiefdoms, then early states. By 7,000 years ago, the first true civilizations were emerging. Sumerian Mesopotamia, with cities of tens of thousands of people, writing systems for record-keeping, specialized bureaucracies, monumental architecture, and complex religious institutions. All of this had developed in just 5,000 years, from the first permanent villages to urban civilizations. But before cities and writing, before kings and temples, there was something else. A cultural explosion that suggests the mental transformation happening during this period was as profound as the economic one. Göbekli Tepe in modern Turkey provides the most spectacular evidence. This site consists of massive stone circles with elaborately carved pillars, showing animals, abstract symbols and geometric patterns. These stones weigh up to 20 tons each. Moving them and carving them would have required hundreds of people working in coordination. Here's what makes Göbekli Tepe extraordinary. It was built 11,500 years ago, before agriculture was fully established in the region. The people who constructed it were still primarily hunter-gatherers. They built a monumental ritual site before they built permanent houses. They invested in creating sacred space before they fully invested in agriculture. This tells us something profound. The transformation wasn't just economic or technological, it was cognitive and spiritual. People were developing new ways of thinking about the world, about their place in it, about their relationships with each other, and with forces beyond human control. The art from this period explodes in sophistication and quantity. Cave paintings had existed during the Ice Age, but post-glacial art is different. More abstract, more symbolic, more clearly religious in nature. Figurines showing highly stylized human and animal forms. Elaborate burials suggesting complex beliefs about death and afterlife. Ritual spaces suggesting organized religions with specialized practitioners. Archaeologists have found evidence of feasting at many early agricultural sites. Not just eating, but ceremonial consumption of food in social contexts. These feasts probably served multiple functions, reinforcing social bonds, displaying wealth and status, creating obligations and alliances. They were the social glue that allowed larger communities to function without the kinship ties that had organized Ice Age bands. Trade networks expanded dramatically. Obsidian, a volcanic glass prized for making sharp cutting tools, was being moved hundreds of miles from source areas to agricultural settlements. Marine shells from the Mediterranean show up at sites in the interior. Copper ornaments appear long before copper toolworking became practical. These trade goods weren't just economically valuable, they were status symbols, markers of connection to distant places and peoples. All of this, the agriculture, the settlements, the social complexity, the artistic flowering, emerged because the ice melted, because the mammoths died and humans had to adapt or perish, because climate catastrophe destroyed the world they had known and forced them to create something entirely new. The irony is almost overwhelming. The greatest climate disaster in human history since the bottleneck, the one that wiped out the megafauna and transformed landscapes globally, was also the event that launched human civilization. If the ice hadn't melted, if the mammoths had survived, humans might still be small bands of hunters following herds across endless grasslands. Instead, that crisis forced innovation on a scale unprecedented in human history. Within 5,000 years, humans went from Ice Age hunters to agricultural villagers to urban citizens of the first civilizations. The melting ice had created the conditions for agriculture. Agriculture created food surpluses. Surpluses created settlements, specialization, social complexity, and technological innovation. By 5,000 years ago, humans were building monuments that still stand today. They were developing writing systems to record their thoughts and histories. They were creating art and literature and religious traditions. They were laying the foundations for everything that would follow: empires and trade networks, scientific inquiry and philosophical traditions, the entire edifice of human civilization. And it all traced back to a simple fact. When the ice melted and the world transformed, humans didn't just survive, they thrived. They took catastrophe and turned it into opportunity. They adapted not just their tools and techniques, but their entire way of life, creating something that would have been unimaginable to their Ice Age ancestors. The age of the hunter was over. The age of the farmer, the builder, the city dweller had begun. And with it came the world we still inhabit today. Here's something remarkable. Scattered across every inhabited continent, separated by oceans and thousands of miles, dozens of cultures tell essentially the same story. A story about water, about floods that destroyed the old world, about survival against impossible odds, about the time when everything changed. The Epic of Gilgamesh, written in ancient Mesopotamia over 4,000 years ago, describes a great flood that covered the earth. The gods warn one man, Utnapishtim, who builds a massive boat and saves his family along with animals and craftsmen. The waters rise for 6 days and 7 nights. When they finally recede, humanity must begin again. Sound familiar? The biblical story of Noah's Ark follows almost exactly the same pattern. A righteous man receives divine warning. He builds an ark. The floods come. Everything is destroyed except what's preserved in the vessel. After the waters recede, the survivors repopulate the earth. But it's not just Middle Eastern cultures. The Ojibwe people of North America tell of Nana Bojo, who survives a great flood by climbing the tallest tree and then creates a new world. The Maori of New Zealand describe how the demigod Tahaki caused massive floods that reshaped the islands. Aboriginal Australians have dozens of flood stories, many describing specific coastal features that are now underwater. The Gunditjmara people of southeastern Australia tell of a time when you could walk to what is now an island before the sea rushed in and separated the land. Chinese mythology includes the Great Flood, which lasted for 2 generations until the legendary Yu the Great drained the waters through massive engineering projects. Hindu texts describe Manu, who builds a boat to survive devastating floods that destroy the world. Greek mythology tells of Deucalion and Pyrrha, sole survivors of a flood sent by Zeus to destroy humanity. For centuries, scholars dismissed these stories as pure mythology, allegories about divine punishment or cultural metaphors about rebirth and renewal. But what if they were something else? What if they were memories? The timing is too perfect to ignore. Most flood myths describe events that happened in the deep past, in the time of ancestors, in the age when the world was different. They describe rapid, catastrophic flooding, coastal inundation, the the loss of familiar landscapes. They talk about refuges, mountaintops and high ground where survivors waited for the waters to recede. This matches exactly what we know happened between 20,000 and 6,000 years ago. The period when ice sheets collapsed and sea levels rose by 400 feet, when meltwater floods periodically devastated river valleys, when coastlines that had been stable for millennia were suddenly submerged in geological eye blinks. The people who experienced these events didn't have writing. They couldn't record their experiences in books or databases, but they had something equally powerful: oral tradition, the ability to preserve important information across generations through stories, songs, and ceremonial teachings. And oral tradition is far more durable than most people realise. Aboriginal Australians have maintained accurate knowledge of events that happened over 10,000 years ago. Linguists and anthropologists working with tribal elders have documented stories describing landscapes that are now 150 feet underwater. Stories about walking to islands that are now separated by open ocean. Stories about freshwater springs that are now submerged offshore. One remarkable example comes from Port Phillip Bay in southern Australia. The Bunwurrung people describe a time when the bay was a flat plain with a river running through it. They tell of how the ocean broke through the heads, the narrow entrance to the bay, and flooded the entire area. Geological surveys confirm this is exactly what happened. Around 10,000 years ago, rising sea levels breached the narrow gap between the headlands and flooded the basin, creating the bay that exists today. The Bunwurrung remembered. Similar stories appear in indigenous traditions from Southeast Asia, where people describe travelling between islands that are now separated by deep water. In the Persian Gulf, where the entire basin was dry land until around 8,000 years ago, when rising seas flooded in through the Strait of Hormuz. In the North Sea, where British and Dutch fishing vessels still occasionally dredge up stone tools and mammoth bones from what was once Doggerland, a populated landscape that connected Britain to continental Europe before the ocean swallowed it. These aren't vague mythological references. They're detailed geographic memories preserved across hundreds of generations. They tell us something profound about human cultural memory. We remember catastrophe. When the world changes dramatically, when landscapes we've known for millennia suddenly transform, we encode that information in our most durable cultural storage system: stories. The flood myths aren't just about the floods themselves. They're about survival. Almost every version includes the same key elements. Someone receives warning, either through dreams or divine communication, or by reading natural signs. They prepare, gathering supplies and seeking high ground. They endure the catastrophe. Then they become the ancestors of the new world, the people who carry forward the knowledge of what happened. This pattern reflects real human experience during the transition. Communities living along coastlines or in river valleys would have seen the changes coming. Not all at once, but incrementally over years and generations. Higher tides, more frequent flooding, familiar landmarks gradually disappearing beneath the water. At some point, the smart groups, the ones who paid attention to patterns, would have moved inland, relocated to higher ground. They would have been the survivors, the ones who carried knowledge forward. But oral tradition only takes us so far. For physical evidence, we need archaeology, and increasingly we're finding it underwater. The field of marine archaeology has revealed dozens of submerged settlements around the world, proof that our ancestors built communities in places that are now beneath the waves. Off the coast of Israel, divers have discovered Atlit Yam, a Neolithic village now 26 feet underwater. The settlement dates to around 7,000 years ago and includes stone houses, a stone circle, and even ancient wells that still contain fresh water. The site was clearly abandoned suddenly. Food and tools left in place. The sea rising faster than people could adjust. In the Black Sea, underwater surveys have found preserved settlements along what was once a freshwater lake. Around 7,600 years ago, rising Mediterranean waters breached the narrow Bosphorus Strait and catastrophically flooded the Black Sea basin. Sea levels in the region rose over 300 feet, flooding thousands of square miles of inhabited coastline. Some researchers think this event might be the origin of the flood myths in Middle Eastern cultures. If you lived through it, you'd certainly remember. The North Sea has yielded extensive evidence of Doggerland, the vast plain that once connected Britain to Europe. Fishing trawlers regularly bring up artefacts, worked flints, bone tools, even occasionally human remains from what was once prime hunting territory for Mesolithic peoples. Beneath the waves lie the landscapes where our ancestors hunted aurochs and red deer, gathered shellfish, and built seasonal camps, all drowned when the ice sheets melted and the North Sea filled in. Off the coast of Florida, archaeologists have discovered sinkholes that were freshwater pools 12,000 years ago, when sea levels were much lower and Florida's coastline extended miles beyond its current position. These pools were apparently used as burial sites by Paleo-Indians. Now submerged in 30 feet of water, they contain some of the oldest and best preserved human remains in North America. Every year new sites are discovered. Underwater surveys using side scans, sonar and multi-beam mapping reveal ancient river channels, now submerged, showing where people would have settled. Stone tools and pottery appear in places that have been underwater for thousands of years. The archaeological evidence confirms what the flood myths preserved. Our ancestors witnessed and survived dramatic coastal inundation as the Ice Age ended. But here's where the story becomes uncomfortably relevant, because we're not just looking at ancient history, we're looking at a preview of our own future. The warming that ended the last Ice Age raised global temperatures by about 4 to 7 degrees Celsius over roughly 10,000 years. That's an average warming rate of about 0.4 to 0.7 degrees per 1,000 years. Now, that might sound slow, but remember, it wasn't smooth. There were periods of rapid warming when temperatures jumped several degrees in just decades. The Younger Dryas termination around 11,700 years ago saw temperatures in Greenland rise by 10 degrees Celsius in less than 50 years. Current global warming is happening at a rate of about 0.2 degrees Celsius per decade. That's 2 degrees per century, 20 degrees per millennium. Nearly 30 times faster than the average rate of warming that ended the Ice Age. We're compressing thousands of years of climate change into mere centuries. The ancient warming was triggered by orbital variations, changes in Earth's position relative to the Sun that gradually increased the amount of solar radiation reaching the northern hemisphere. It was natural, predictable, according to astronomical cycles that have been operating for millions of years. Current warming is triggered by greenhouse gas emissions, carbon dioxide released from burning fossil fuels. It's anthropogenic, human-caused, and it's happening at a rate that has no natural analogue in the entire ice core record. Ice, cores drilled from Antarctica and Greenland, preserve atmospheric samples going back 800,000 years. They show us exactly what the atmosphere contained during multiple glacial cycles. Carbon dioxide levels during ice ages typically hovered around 180 parts per million. During warm interglacial periods like the one we've been living in, levels rose to about 280 parts per million. This 100 ppm variation drove the entire cycle of ice ages and warm periods. Current atmospheric carbon dioxide levels exceed 420 parts per million. That's 50% higher than the highest natural levels recorded in the past 800,000 years. We've pushed the atmosphere into a state that hasn't existed since the Pliocene epoch, over 3 million years ago, when sea levels were 50 to 80 feet higher than today, and the Arctic was ice-free during summers. The ancient climate data teaches us something crucial about tipping points. Climate doesn't change smoothly and gradually. It lurches. Systems remain stable for long periods, absorbing changes and maintaining equilibrium until suddenly they don't. They flip to a new state, often very rapidly. The ice core record shows this clearly. Temperature rise isn't a smooth curve. It's a staircase. Long periods of relative stability interrupted by sharp jumps. These transitions happen when feedback loops kick in. ice melts, exposing dark rock or ocean that absorbs more sunlight, which melts more ice. Permafrost thaws, releasing methane, which warms the atmosphere, which thaws more permafrost. Ocean currents shift, changing how heat is distributed globally, which triggers further shifts. During the deglaciation, the climate system hit multiple tipping points. Each one amplified the warming, accelerated the ice loss, drove sea level rise faster. The scary part is that we can see similar tipping points approaching in our current climate. The Greenland ice sheet is losing mass at accelerating rates. Arctic sea ice is declining far faster than models predicted. Permafrost across Siberia and northern Canada is thawing and releasing carbon. Rainforests are experiencing more frequent droughts that kill trees and release stored carbon. The ancient warming was ultimately limited by negative feedbacks. Eventually the ice sheets melted completely, sea levels stabilised and the climate reached a new equilibrium. But it took over 10,000 years, and along the way it eliminated most of the Ice Age megafauna and forced massive human migrations and adaptations. We're triggering similar changes, but faster. Much faster. The question isn't whether sea levels will rise. They will. Ice sheets are already losing mass. The question is how fast and how far. Conservative estimates suggest 3 to 6 feet of sea level rise by 2100. More aggressive projections based on potential ice sheet instability suggest 10 feet or more is possible. Either scenario will inundate coastlines where hundreds of millions of people currently live. Our ancestors adapted to rising seas by moving inland, to higher ground, to new territories. They could do this because human population was tiny, maybe 5 to 10 million people globally at the end of the Ice Age. Most of the planet was empty. You could abandon a flooded coastal settlement and walk for a week to find unclaimed territory. We don't have that option. Earth now holds over 8 billion people. Most coastal land is already occupied, cultivated, built upon. Climate refugees in our future won't be moving into empty wilderness. They'll be competing for space in regions already at carrying capacity. The ancient climate transition also teaches us about ecosystem fragility. The megafauna extinctions weren't just about human hunting pressure. They were about ecosystems reorganizing, food webs collapsing, the relationships between species that had been stable for hundreds of thousands of years suddenly breaking down as climates shifted and habitats changed. We're seeing early signs of similar reorganization today. Coral reefs bleaching as ocean temperatures rise, forest die-offs as drought patterns shift, fish populations migrating toward the poles as tropical waters warm beyond their thermal tolerance. Species that can't migrate or adapt fast enough simply disappear. Once extinct, they're gone forever, just as mammoths and giant ground sloths and dire wolves are gone forever. The fossil record shows that major extinction events are permanent. The species lost during the End-Pleistocene extinctions never came back. New species eventually evolve to fill empty ecological niches, but that process takes tens of thousands to millions of years. On human timescales, extinction is forever. But perhaps the most important lesson from the ancient climate transition is about human adaptability balanced against human suffering. Yes, our ancestors survived. They adapted their technologies, modified their hunting strategies, developed new food sources, and eventually thrived in the post-glacial world. The agricultural revolution, the rise of civilization, everything that followed was built on the foundation of post-glacial climate stability. But the transition period was brutal. Archaeological evidence shows increased violence, resource competition, population crashes, and the abandonment of entire regions. The genetic bottlenecks that show up in human DNA around this period indicate our population went through serious contractions. Many groups didn't make it. We're descended from the survivors, but survival came at enormous cost. The flood myths preserved in cultural memory aren't just about physical inundation, they're about loss. The loss of familiar landscapes, traditional territories, ways of life that had persisted for generations. They're about trauma, the trauma of abandoning ancestral lands, of watching the places you knew disappear, of uncertainty about whether you'd find new homes, new hunting grounds, new sources of food and water. Our ancestors survived by being flexible, mobile, and few in number. They could move when they needed to. They had technology simple enough to rebuild from scratch if necessary. They lived in groups small enough to relocate relatively easily. These advantages allowed them to weather a climate transition that would have destroyed less adaptable species. Modern human civilization has different strengths and different vulnerabilities. We have vastly more sophisticated technology. We understand climate science. We can model future scenarios and potentially prepare for them. We have global communication networks, transportation systems, and institutional structures that could theoretically coordinate large-scale adaptive responses. But we're also far less mobile. Our infrastructure, cities, farms, factories, can't be easily relocated. We're dependent on complex supply chains that span continents. We've organised ourselves into nation-states with rigid borders and competing interests. And we're numerous, 8 billion people, all needing food, water, shelter and resources. The ancient climate transition took thousands of years. That gave ecosystems and human societies time to gradually adjust. Our current climate forcing is happening so fast that adaptation will be difficult for natural systems and human societies alike. We're not facing a gradual transition over many generations. We're facing dramatic changes within single lifetimes. The stories preserved in flood myths remind us that our ancestors lived through times of dramatic environmental change. They witnessed their world transform. They adapted, survived, and eventually thrived. But the stories also remind us that these transitions were catastrophic. They were events so traumatic that they became embedded in cultural memory for thousands of years. Warnings passed down generation after generation. Remember the floods. Remember that the world can change. Remember that survival requires preparation, flexibility, and sometimes painful choices. We're now living through our own climate transition. We have advantages our ancestors lacked. Knowledge, technology, global cooperation, at least in theory. But we also face challenges they never encountered. A crowded planet, complex interdependent systems, and changes happening faster than natural adaptation can keep pace with. The ice cores and ancient climate records aren't just scientific curiosities. They're textbooks. They teach us that Earth's climate is sensitive, capable of rapid and dramatic shifts. They show us what tipping points look like, how feedback loops amplify small changes into massive reorganizations. They demonstrate that extinction is real and permanent. They prove that sea level rise, when it starts, can continue for thousands of years, even after temperatures stabilize. Most importantly, they remind us that climate change isn't an abstraction. It's not just about temperature graphs and computer models. It's about landscapes transforming, coastlines drowning, ecosystems collapsing, people migrating, communities disrupted, ways of life ending, the very real human consequences that our ancestors experienced and preserved in their most enduring stories. The world has changed dramatically before. It's changing dramatically now. The question isn't whether we can survive climate change. Our species has proven its adaptability. The question is what kind of world we'll inhabit, how much we'll lose along the way, and whether we'll heed the warnings encoded in ancient memories and modern science alike. The floods our ancestors survived left marks that persist to this day. Drowned coastlines now explored by archaeologists, genetic signatures of population bottlenecks, cultural memories embedded in mythology, lessons preserved in ice cores and sediment layers, echoes of a time when the world transformed and nothing would ever be the same. We're creating echoes of our own. Future generations, assuming we successfully navigate the coming transition, will study our time. They'll analyse our climate data, excavate our cities, read our records. They'll ask what we knew, what we did, and what we lost. The ancient transition ended one world and began another. Ours will do the same. What remains to be determined is what we preserve, and what we're willing to let go. So, here we are, the endpoint of one of the most dramatic transformations in Earth's history. 12,000 years ago, our planet was locked in ice. Massive glaciers covered a third of the land surface. Sea level sat 400 feet lower than today. Mammoth herds thundered across frozen steppes that stretched from France to Alaska. Saber-toothed cats prowled landscapes that would later become shopping malls and city centres. Then, in what amounts to a geological eye blink, everything changed. The ice melted, seas rose, coastlines drowned, entire ecosystems collapsed and reformed. The megafauna that had dominated the planet for millions of years disappeared, victims of climate chaos and human hunting pressure they couldn't withstand. Within just a few thousand years, the frozen world that had defined the Pleistocene was gone, replaced by the warm, green, relatively stable planet we inherited. The Holocene, our epoch, the world we think of as normal, but there's nothing normal about it. The last 12,000 years represent one of the most stable climatic periods in the last million years of Earth history. The wild temperature swings that characterize the Ice Age, those dramatic shifts between frozen and mild that could happen within decades, mostly stopped. Seasonal patterns became predictable, sea levels stabilized. The climate settled into patterns that, give or take some regional variation, have remained remarkably consistent. This stability made everything else possible. You can't develop agriculture when the climate might shift catastrophically every few generations. You can't build permanent settlements when sea levels might rise 20 feet in a century. You can't accumulate the kind of surplus resources necessary for complex civilization when you're constantly scrambling to adapt to new conditions. But our ancestors, products of the bottleneck shaped by hundreds of thousands of years of environmental pressure, they were ready. They had the cognitive flexibility, the technological innovation, the social organization, and the communication skills necessary to exploit this new stable world. Within just a few thousand years of the Ice Age ending, they had developed agriculture in at least 7 independent locations around the globe. The Fertile Crescent, the Yellow River Valley, Mesoamerica, the Andes, Sub-Saharan Africa, New Guinea, Eastern North America. Everywhere modern humans lived, they figured out how to cultivate plants and domesticate animals. From there, everything accelerated. Permanent settlements became villages. Villages became towns. Towns became cities. Agricultural surplus allowed specialization. Not everyone had to spend all their time gathering food. Some people could become craftsmen, priests, soldiers, administrators. Social hierarchies developed. Writing systems emerged to track resources and record information. Trade networks expanded to move goods across continents. Within 8,000 years of the ice sheets retreating, humans had gone from small bands of hunter-gatherers to building ziggurats in Mesopotamia and pyramids in Egypt. The same species that had survived on scraps during the Ice Age was now creating monumental architecture, complex bureaucracies, and sophisticated art. The transformation was unprecedented in the history of life on Earth, but it came at a cost. Those magnificent creatures that had survived multiple ice ages, they couldn't survive us in a warming world. The mammoths, mastodons, giant ground sloths, saber-toothed cats, dire wolves, short-faced bears, all gone. Some vanished because their ice age habitats disappeared. Others fell to human hunters who had become too efficient, too numerous, too technologically advanced. Either way, the result was the same: extinction. Entire landscapes were lost too. The Bering Land Bridge, that crucial corridor that had allowed humans to reach the Americas, drowned beneath rising seas. The vast continental shelves that had provided rich hunting and gathering grounds along every coast submerged. The mammoth steppe ecosystem that had stretched across the northern hemisphere, replaced by forests and tundra. Ways of life that had sustained human populations for tens of thousands of years, erased in centuries. Our ancestors mourned these losses. We know they did because they remembered them. Cultural memories of great floods, of lands swallowed by the sea, of a time when giants walked the earth. These stories appear in oral traditions around the world. The Aboriginal Australians remember when you could walk to Tasmania. The indigenous peoples of Southeast Asia recall when the islands were connected. Flood myths from dozens of cultures preserve fragments of genuine historical memory, distorted and mythologized over thousands of years, but rooted in real events that shaped human consciousness. We are the inheritors of all of this. The world we live in, the stable climate we've enjoyed, the agricultural systems that feed 8 billion people, the cities, the technologies, the entire structure of modern civilization, all of it built on the foundation of that post-Ice Age transformation. We are the descendants of the survivors, the ones who made it through the bottleneck, who adapted to the thaw, who learned to thrive in a world that had stopped trying to kill them at every turn. But we're also facing our own transformation now. The climate stability that made civilization possible is ending. Not through natural cycles this time, but through our own actions. We're conducting an experiment on our planet's climate system that will determine whether we've inherited enough of our ancestors' adaptability to survive the changes we've triggered. That's a story for another time. For now, rest easy knowing that humans have survived worse, much worse. We carry the genetic legacy of those 280 individuals who refused to give up when everything seemed lost. We have the cognitive tools, the technological capabilities, and the communication systems they could never have imagined. If they could make it through 117,000 years of environmental catastrophe with nothing but stone tools and determination, maybe, just maybe, we can figure out how to navigate what comes next. If you enjoyed this journey through deep time, consider liking this video and subscribing for more historical deep dives. Drop a comment and let us know where you're listening from and what aspect of Ice Age history fascinated you most. The megafauna extinctions, the flood events, the human adaptations. Until next time, sleep well. Dream of mammoths and melting glaciers. Remember that you're part of the longest survival story ever told.